All right. Let's look at astronomical distances. No, I don't want that one. That one's too wide. There's really only two of them I'm really concerned with. I think the lecture went over three, but there's only two you really need to know. And one is for intra-solar system distances. And what does intra mean? Intra. Intra means this is intra-classroom. Out there is inter-classroom. Intra is what? Within. So when you talk about intra-solar system distances, what was the unit of measurement? Take it off, please. What's the unit of measurement? An astronaut, go get a pass.
What? I was only 2 minutes late.
Because you need a pass.
What is it?
Astronaut. Jeez. Now, let's see, where am I? The first one's an astronomical unit. And an astronomical unit is the distance between what and what?
Atmosphere.
An AU is the distance between what and what?
Sun and Earth. Distance in
From the sun to the Earth. 93 million miles. I don't know how many kilometers it is. But it's that distance. So when we say something is 2 AUs from Earth, that means it's 2 times the distance from the Earth to the sun away. So astronomical units are used within the solar system. The other one is called a light year. The light year is interstellar. And what do we mean by interstellar? Inter is between. Stellar means stellar? Stars. And so when you talk about interstellar distances, you're really talking about a light year, or how far light can travel in 1 year. We know it can travel 3 times 10 to the 8th meters per second, but then you have 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a year. It ends up being, I don't know, into the trillions. So that is a distance unit used for, measuring the distance of stars. The last one I put on there was parsecs, and that gets into really intergalactic and deep space, and we're really not going to worry ourselves with that.
You also said warp speed.
Oh yeah, warp speed for all you Star Trek fans. Captain Kirk, fire up warp speed. Captain, my engine's overheating. So really, the two big ones though are AU and a light year.
What's an AU?
Astronomical unit.
Yeah, it should be right in your notes. All right, open up to a new page and call it gravity.
Somebody got a paper I can borrow?
Open up a new page and call it gravity.
For the notes, can I just do it in Google Docs? Print it?
You need it in a notebook. All right. I need to thoroughly embarrass somebody.
Me?
No. No.
Come on, why?
Caleb.
What about
I've already been embarrassed before. I can handle it.
What?
Embarrass
I
Caleb.
did.
Huh?
Embarrass him.
Come on, Bruce,
No.
I'm not ashamed.
No. Who can I embarrass in here?
No.
Bella.
No.
You?
No.
All right, Austin. Yeah, he's. Is there a physical attraction between me and you?
Oh yeah. Good.
No, that came right out. No. Yes, there is. Yeah. How about between you two? Is there a physical attraction between you two?
Yes, there is.
Yeah.
There is.
Inform it.
Yes, there is.
Is there?
Yes, there is.
Yes.
How about one here?
Yes.
Oh, we're being recorded.
How about you guys? You just figured that out?
I look over here and I see
Where have you been?
I've been in the office.
Oh, how about you guys?
Yes.
Yeah, and that attraction's called what? Gravity. So really, there is between everybody, everything, in fact, anything that has what? Mass. Anything that has mass is going to have that. Well, the gravitational force is really between two masses. So, you got all sorts of objects in here, and there's a gravitational pull or attraction or force between every two objects or every object in here. So why isn't things flying off the bookshelves and all sorts of stuff? There's what? There's not. Yeah, but what about it? So why is it pulled down? So why isn't things flying off the shelves and attracting to each other?
Magnetic.
No, that's magnetic fields. We're talking gravitational. What's the overriding gravitational force here? The Earth. The Earth is much, 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 much larger than any of us. So that is the overriding gravitational force. So one aspect of gravitational force, it depends on what of the object? The mass. The greater the mass, or the greater the mass is, the greater the what? The gravitational force. Larger mass / masses the greater force. The Earth definitely is going to overpower any type of gravitational force that objects on the surface may have towards each other. While the Sun has a much, 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 much larger mass than the Earth, so why aren't we drawn into the face of the Sun? Huh? Oh, there's gravity. There's gravity. There's gravity in space. Yeah. All right. Well, and this... Yeah, we're going to get into that a little bit more tomorrow, but why aren't all the planets just sucked into the sun? There's a lot of mass there, but what's the other aspect of gravitational force? We're going to get into that tomorrow. I mean, what else affects gravitational force? That's why we're not. Yeah.
Distance?
You got it. What about distance? Give me a statement. Yeah.
I don't know.
Well, we don't fly into the sun because we are what from the sun?
Far.
Far. So the greater the distance, the less gravitational force. When you start having more and more distance between objects, that gravitational force is going to decrease. So when you think about gravitational force, you actually got two aspects to worry about, two characteristics. The mass of the objects and the distance between them. Now tomorrow when we look at the solar system, we'll look at speed and vectors on that. But for right now, just remember, those are the two interplays for gravitation. We're going to get into it a little bit more later, but that's what's happening there.
What are we taking the test on?
I don't know yet. Okay, I've got a lacrosse ball. They have a tendency to leave them on the track all the time. And a piece of paper. Which one's got more mass? Yeah, well, lacrosse ball, definitely. If I were to drop these two, what's going to pull them to the surface of the Earth?
Gravity.
Gravity. So which one's going to
Go faster?
which one's going to hit first?
The ball.
Ball's going to hit first?
Yeah. Unless you put the ball on top of the paper.
Oh, I could, but I don't want to do that. What about air resistance? Stops what? It stops gravity?
Crumple the paper up.
Paper's gonna fall first.
Huh?
The paper's gonna hit first.
You just told me the mass of this was greater.
Well, you just crumple the paper up.
The mass is,
Huh?
the mass is still the same.
I don't know. Okay, I'm not that smart.
That's pretty good.
The ball still wins.
Told you.
But the only thing stopping the paper from falling at the same rate is what? Air resistance, yeah. If I could get this so the air resistance gets to be less and less and less. That's pretty darn close.
Catch the ball, Riley.
So tell me something about how fast an object falls and its mass.
You should drop it one more time so we can see it again.
Tell me something about how fast an object will fall and its mass. Does it matter?
No.
No. So mass has no bearing on how fast an object will fall. And you're right. The only thing that slows things down in the atmosphere is air resistance.
So smart, Louise.
Yes, it is. He's right on money with that. All right, open up your QPO. You've probably noticed this QPO does not have all the little Q's. This is our third one, so we're kind of beyond giving you little cues on here. Okay, on this one, gravitational acceleration. And again, the overriding or guiding question, do all objects accelerate at a constant rate during free fall above the Earth's surface?
Yes.
All right, but you don't answer that question. You kind of do, but you answer it through the QPO. The personal knowledge, again, you can. That's pretty straightforward. You need to do the scientific investigation knowledge on this part. You should have probably a minimum of 10 terms. Do not use a dictionary for the terms. You guys are way beyond just putting dictionary definitions in here. Again, you can do your prediction, and then your investigation plan, which is really your experiment. You need to come up with a detailed investigation plan. I'll tell you right now, experience has shown that you're all going to probably end up in a pretty similar investigation plan. But you need to come up with something that is detailed. And then once we have your investigation plan, we will perform your investigation plan, and then we'll go on. So this one, I don't have a due date on it yet. I don't know how long we'll give this one out here. But you need to work, yeah, it probably will be. But you need to work on this when you have time to do it. Like today, you're going to have the rest of the hours to start working on this. You can work, I guess, anywhere from 2 to 4 people in a group. You, just like we did the other QPOs. Well, you got to start investigating Do all objects accelerate at the same rate during free fall?
Oh, that's just a question?
Right, that's what you're going to investigate. So you've got rest of this time to get working on it.